Welcome to the deep dive. Today, we're trying to cut through some of the noise around large language models, LLMs. We're diving into their, well, often fascinating, but sometimes pretty puzzling world. And our guide for this is quite a dense but really insightful NBER working paper. It's called Large Language Models, an Applied Econometric Framework. Now, you've probably heard about LLMs. I mean, they do some astonishing things, right? Writing poetry, acing tests. But they also fail in some really surprising ways. So what does all that mean for, say, researchers, people trying to use them for, serious empirical work? Can we actually trust these incredibly powerful but, yeah, unpredictable tools?
Well, what's really crucial, I think, that the paper proposes is this idea of contracts for LLMs. Think about it like the contracts we already have in econometrics for standard tools like OLS, ordinary least squares. Those clear rules, the assumptions a researcher have to defend to say their conclusions are valid. We need something similar for LLMs. And it's especially important because, as the authors point out, we often have to treat these things as a black box. We just don't know the inner workings.
Okay, yeah, that makes a lot of sense. It's like buying a complex machine you can't really open up, so you need a really solid warranty or contract about what it does. So the paper digs into two main ways researchers want to use these things: prediction problems and estimation problems. And it seems the rules for using them reliably are, well, pretty strict. Let's start with prediction then. This is where you'd use an LLM to predict some economic variable based on text, like, I don't know, predicting stock prices from news headlines, or maybe figuring out if a congressional bill will pass just from its description. Sounds powerful.
Right? Incredibly powerful potential. But it immediately raises the key question, when is that actually valid? And the paper really nails it down to one single critical condition: no training leakage.
Mm.
Basically, it means zero overlap between the LM's huge training data set, which we often can't even see, and your specific research data set. Because if the LLM has already seen your test data during training, well, its predictive power isn't real. It's just memorization.
And this is where it gets really interesting because the paper actually shows empirically that this no training leakage thing, it's violated pretty often when people just use LLMs naively. They looked at congressional legislation data, huge data set, like 400,000 bills, 1973 to 2016. And yeah, GPT-4 was great at predicting outcomes, 91, 92% accuracy, impressive stuff. But, and this is the big but, when they tested it more closely, GPT-4o exactly completed the first half of the text for 344 different bills. That just screams memorization. It's seen this stuff before. That's leakage.
hmm And they found a similar thing in finance, too. Used about 10,000 news headlines from 2019. GPT-4 spat out 60 of those headlines verbatim, exactly reproduced them. Again, suggests memorization. And this creates what they call look-ahead bias. The model might be using information from the future relative to the text it's supposed to be analyzing. That completely messes up your predictions.
Okay, so the obvious thought is, can't you just, you know, tell the LLM in the prompt, hey, ignore data after this date? Does that fix it?
You'd think so, wouldn't you?
Hmm.
But the paper found that prompt engineering, just telling it things, it doesn't really solve the training leakage problem. GPT-4o still memorized text even with those date restrictions. And the reason is, prompts only influence the text generator part you interact with. It doesn't change the underlying model, the training algorithm itself, where that memorization is baked in.
Right, it's like telling a student who memorized the textbook not to use the textbook during the exam, but they still have it all memorized. So if prompts don't work, what's the practical advice? How do researchers actually ensure no leakage?
The paper is quite clear here. To be credible, you really must use open source LLMs, models where the training data is documented or where there's a fixed timestamp and, we haven't updated past this date. Things like the Llama family or Stories SLM. Those are the examples they give. And conversely, they strongly advise against using closed models, like OpenAI's GPT's, Anthropic's Claude. Because their training data is secret, they get tweaked constantly. You just cannot know if leakage happened. They even found results for the same prompt changed month to month on GPT-4.
Wow. So transparency is basically the price of admission for using LLMs reliably in prediction tasks for research. That seems really important.
Yeah.
Okay, so let's pivot then. What about the other main use case, estimation problems? This sounds like using the LLM to automate measurement, like getting it to label news sentiment positive, negative, or maybe figure out the policy topic of a bill, and then you use those labels in your actual analysis downstream.
Yeah, that's the idea. And the, let's say, naive way to do it is just to plug those LLM outputs straight into your regression or whatever analysis you're doing. But here's the catch. That's only valid if the LLM's outputs have zero measurement error, which means the LLM has to perfectly replicate whatever existing measurement process you're trying to automate, like, say, human coding. That's a really, really strong assumption. And we know from benchmarks like GPT-4o gets about 86% on MMLU. Perfect performance just isn't what these models do.
And they show this isn't just theoretical, right? The paper has some pretty stark results on how brittle this can be in
Oh,
practice.
absolutely. Stark is the right word. Take the financial news headlines again. They had different GPT models like 3.5 Turbo, 404, and Mini try to label sentiment. Use 9 different prompts for each. And the agreement between the different LLM outputs, sometimes as low as 79%. But here's the really critical part. That variation, just from changing the prompt or the model, it caused huge swings in the downstream results, like predicting stock returns based on positive sentiment headlines.
Yeah.
The G statistic went from almost -6 all the way up to +2.
Whoa, -6 to +2, just from tweaking the LLM prompt.
Exactly. That
Yeah.
completely changes your conclusion about whether sentiment matters.
Okay, that's finance. What about the congressional bills? That feels a bit more objective, maybe. Labeling policy areas?
Similar story, unfortunately. They used GPT 3.5 Turbo and GPT 4o, prompted them 12 different ways to label the policy topic.
Yeah.
Again, substantial disagreement between the different labeling attempts. And that disagreement directly led to big changes in the downstream regressions. Looking at how policy relates to the sponsor's party or ideology, the results changed in magnitude, significance, sometimes even the sign flipped.
What I find fascinating here is the point about accuracy. The paper says even when the LLM labels were, on average, almost as good as human labels, the downstream results were still all over the place. So just being pretty accurate isn't enough.
That's the key insight, really. Average accuracy alone doesn't cut it for justifying this naive plug-in approach. That brittleness means even small, seemingly acceptable errors can get amplified in the downstream analysis in unpredictable ways. So, yeah, pretty good is not good enough here.
Okay, so if just plugging in the LLM outputs is unreliable, potentially leading you way off track,
Yeah.
what's the fix? Do we just give up on using LLMs for estimation?
No, definitely not give up. There's a practical solution, and it's actually based on pretty standard econometric practice. It involved collecting a small benchmark or validation sample.
Ah, okay. So you mean you let the LLM label your whole big data set because that's cheap. But for a small random subset, you also get the gold standard labels probably from humans, which is expensive. And then you use that small human labeled set to figure out how the LLM messes up its specific error pattern
Mm,
and correct for it, like calibration.
precisely. You calibrate the cheap, noisy LLM labels using the small set of expensive, accurate human labels. The paper simulations with the congressional bills show this works really well. Remember those naive regressions where the confidence intervals were way off? Like GPT 3.5 only covered the true value 38% of the time. Well, using the bias corrected approach, Even with just a 5% validation sample, they got reliably unbiased estimates. The coverage jumped to around 93%, which is what you want.
Okay, that's a huge improvement from a small validation set. And then there's this idea they call a free lunch, which sounds almost too good to be true. The claim is that the LLM, once you debias it with that validation data, doesn't just save money. It can actually improve statistical precision compared to only using the small human sample.
Yeah, it does sound a bit like magic, but it makes sense.
Hmm.
The LLM provides information across your entire data set. The validation data tells you how to interpret that noisy information correctly. So you're leveraging the scale of the LLM and the accuracy of the humans. It effectively amplifies the value of that small, expensive validation set. Your human effort goes much further.
But what if you just can't get that benchmark data? Maybe it's impossible or prohibitively expensive even for a small sample.
The paper's advice is pretty blunt then. Don't use the LLM outputs for estimation without it. They argue against trying to justify it, saying, oh, there are no errors. Just flies in the face of all the performance benchmarks we see. Trying to statistically model the errors without benchmark data is, they say, heroic, basically, a long shot given the black box nature. And just redefining your research question to be about the LLM's output rather than the real-world concept, that makes your findings totally dependent on that specific LLM version and vulnerable to any future updates.
So this benchmark data seems crucial for replicability too, not just getting the same numbers out of the LLM again, that's mechanical replication, where open source models help, but for conceptual replication, knowing that different models or prompts are still pointing towards the same underlying truth, you need that benchmark data as an anchor.
It's exactly right. That benchmark data provides the ground truth link. It ensures your finding isn't just some artifact of GPT-4's specific prompt interpretation on a Tuesday in May. It helps ensure you're actually measuring the economic concept you care about.
Okay, moving beyond prediction and estimation, the paper also touches on some more, let's say, novel uses. Things like automated hypothesis generation or even simulating humans. That sounds like science fiction territory.
It does a bit, but the framework still applies. Take hypothesis generation, asking an LLM for new ideas, maybe new instrumental variables. The no training leakage rule pops up again. You want new ideas, right? Not just things the LLM has already seen in its training. Like if you ask for an IV for education and it gives you distance to college, well, that's a classic. I probably just memorized that. Not helpful for novelty.
So again, you'd prefer an open source model where you have a better sense it hasn't just read every econometrics paper ever published.
Ideally, yes. Or at least be very cautious about the novelty of suggestions from closed models.
And the human simulation idea. Using LLMs as what? In silico participants in experiments or surveys.
Yeah, it's a fascinating application, and it maps directly back to an estimation problem. The LLM's response is essentially trying to measure the average human response to your survey question or experimental setup. But the paper points out the same brittleness concerns. LLMs don't perfectly mimic humans. They sometimes give false positives in psychology experiments, or they don't accurately replicate results from opinion polls. They aren't perfect human clones.
So does that mean using LLMs to simulate people is a non-starter?
No, not necessarily a non-starter, but you can't just swap out humans for LLMs wholesale. You still need validation data from real human subjects. Think of like the estimation problem again. LLMs can't fully replace humans, but they can potentially amplify a small validation sample of real human responses. This could be really useful in situations with tons of experimental conditions, like that Choices 13K data set they mentioned, over 1 million choices studied. Maybe an LLM could generate responses for all conditions, but calibrated against real human data from a subset of those conditions.
Okay, so wrapping this all up then, LLMs are clearly amazing tools. They can expand what we can do in empirical research, especially with text. Huge potential. But, and it's a big but, we have to be really smart and rigorous about how we use them.
Absolutely. It boils down to two main things based on this framework. For prediction, guard against training leakage. That means favoring transparent open source models where you can actually check for this. And for estimation,
Mm.
you really, really need that benchmark data. You have to collect it to debias the LLM outputs. It's not about replacing humans, but amplifying human effort.
Yeah, the paper really drives home that we as researchers are now consumers of these incredibly powerful AI tools, but we're often totally blind to how they work inside. But this framework gives us a way to create meaningful contracts for using them, ways to ensure our research stays robust and, actually correct.
It's a good reminder, isn't it, that these tools are powerful, but understanding their limitations and applying them critically is where the real value comes from, especially with so much information and misinformation out there.
Definitely. Which leaves us with a final thought for you, our listener, to maybe mull over. As these AI tools get even more powerful, maybe even more opaque, how will these contracts we need for rigorous research have to evolve? What new assumptions might we need to start thinking about and defending? Thank you for joining us for this deep dive. Hopefully, you feel a bit more grounded in the exciting but complex future of LLMs and research.